Hello. Hello, good evening all. I am Saurabh and I welcome all of you to this session for the NPTEL course Applied Computational Fluid Dynamics. And I think we can start now. But before starting, can anyone please confirm that my screen is visible and I am audible?
Yeah, it's visible and audible. And can I ask you if this recording will be available for us?
Yes, I am uploading these on YouTube and the links are there in NPTEL page.
Oh,
Maybe the
thank you.
last lecture, last lecture may not be uploaded. I will upload the remaining lectures, but everything is being uploaded in the YouTube. And whatever I'm writing on my iPad, all these PDFs and annotations are also there in a separate link.
Okay, excellent. Thank you very much.
Thank you. Okay, so this is our session 4. And in this session, we will try to solve some problems which are related to classifications of partial differential equations and some numerical techniques. Okay. Okay, so I think in the lectures you must have studied about the partial differential equations, right? Their types, hmm, order, degree, all these definitions, right? So the basic
Yes,
difference, so the basic difference between a partial differential equation and a ordinary differential equation is that ordinary differential equation has one variable, right? So your let us say velocity field that will depend on only one variable. But if there are more than one variable on which these temperature or velocity they are dependent, so the equations are partial differential equations, right? So for example, you have a temperature distribution. So that temperature distribution can be a function of, a space. So space means two coordinates, x and y, and that can be also a function of temperature, right? So there are many variables. So in that case, what we have partial differential equations. And most of the times, when the partial differential equations are, non-linear and second order, most of the time they are not, they cannot be solved analytically, right? Sometimes in some special cases, under some special boundary and initial conditions, they can be solved analytically, but most of the cases in general, they cannot be solved, right? So that is the reason we are using some numerical techniques, right? Because we don't have the exact solutions. And we also don't know that whether the exact solution exists or not. Okay. So before starting, what we do, we classify the partial differential equations in some categories. And what are those categories? First of all, on the basis of linearity, right? So whether the partial differential equation is linear or not, right? So there are quasi-linear equations. So in quasi-linear equations, the derivative of highest order, they are linear, right? And other are semi-linear. So in semi-linear, the equation should be quasi-linear, but the coefficient of the highest order derivative, they should not contain dependent variable or their derivatives, right? And there are some non-linear equations as well. So non-linear equations are basically those which are not quasi-linear. And the simplest ones are linear one, right? So in the linear one, all the variables and their partial derivative, they occur linearly, right? So with this background, so we can start our discussion. Okay. So starting with question number 1. Question number 1 says the viscous Berger equation in conservative form can be written as. So what are these Berger equations? Hello.
I think it's the fourth one.
Huh?
Dou U by dou t plus u dou u by dou x equal to, so if we take u inside the bracket, so it becomes u square by 2.
Okay, so the answer is correct, of course. Option, the answer you are telling, that is correct. Okay, so you should know what are these Berger equations. Okay, and what is the conservative form? You know what is the conservative form?
Yes, I mean we take all the variables inside the bracket.
Yes, inside the bracket. Bracket means inside the inside the
Differential,
uh,
differential.
diffusion term, right? Sorry, inside the gradient, right? Right there, right? So basically, conservative form is basically derived from directly from the conservative conservation laws, right? So this is temporal term. Okay, so the time rate of change, and
Spatial term, spatial gradient.
this basically represents what is going inside the boundaries and what is coming outside the boundaries, right?
Yes, sir.
And this term means the diffusion term. Okay, so this is the conservative form of the Berger equations. Okay, so these equations are important because they are second order, and many times our fluid mechanics equations can be simplified to these equations. Okay, and these can be solved analytically sometimes. There are some special and simplified version of our more general Navier-Stokes equations. Anyways, coming to question number 2. So question number 2 says, so there is some equation, and it is asking that this equation has how many real characteristic roots. So I hope you are familiar with this notation. For example, if this uxx is written, so this means you are taking the derivative, partial derivative with respect to x twice. Okay, so this is basically dou by dou x square of u. Okay, and so on. So this is the equation, and it is asking how many real characteristics roots are there.
B square minus 4c is coming to be 0. So only one real characteristic root.
Right. So first of all, we will have to write, for example, a uxx plus b uxy and so on, and then uh, check the determinant, right? B square minus 4ac, right? Hello.
Yes, sir.
Okay. So what is a? How we write? We write like this: a uxx plus b uxy plus c uyy and some other terms is equal to 0, right? Hello.
Yes, sir.
Okay. So what is a here?
Sine square x.
Sin square x, and b c
Cos square x.
c is what?
Cos square x.
cos square x. So what we need to find now?
B square minus 4AC.
B square minus 4ac. So B is sine 2x and right. To 0. So when this is 0, then which type of equations are these?
Elliptic.
And how many real characteristics it will have?
1.
So if it has one real characteristic roots family, then it is elliptic. Are you sure? It is parabolic, no? Parabolic equations have one real characteristic family, right? And elliptic, they don't have any real characteristic family. Okay. And hyperbola, they have two, right?
Yes, yes.
So this is not elliptic. This is what? Parabolic. And since it is 0, so this means how many roots? One. One real characteristic. Root. So correct option is option A, right?
Yes, sir.
And what does this characteristic roots or characteristic curves mean? So have you any idea? Has this been discussed in the lectures? Well, what I mean is that many times you are encountering these terms: elliptic, parabolic, hyperbolic. So is there anything which has some shape like a hyperbola or ellipse or parabola, some geometric stuff that looks similar in the shape? Hmm? Like many times we do have this confusion. Like if you say that this is elliptic, for example, or this is parabolic, for this case, this is parabolic. So what the parabola is doing here? Is there any some parabola or ellipse? Some geometric curves are there which looks like parabola?
So I think it is like actually there is no parabola or hyperbola, but it is analogous to the conic section as far as I understand.
Yes, you're right. Uh, there is no real curve. Okay, so there is no real parabola. Okay, so basically when you compare this equation to your conic section equation, right? Your second order polynomial, and when you compare, then you do find that when this determinant is 0, then you have parabola. Okay, so one analogy you can make here is that the parabola is, for example, this is a parabola. Okay, so this has one opening. Okay, so this has one opening. So this means there will be only one characteristic curve and the information will travel along that characteristic curve. Okay, and for ellipse, there is no real uh, characteristic
Open.
line. Okay, that is not open, that is closed one. Okay, so in that case, information will travel immediately, right? So if there is one disturbance at any point, that will affect all the points in the space immediately. Okay, and hyperbola has two openings, you can say. So there will be two families of characteristic curves. Okay, so don't think that these characteristic curves are in the shape of parabola or ellipse or hyperbola. That is not the case. Okay, the thing is how many families are there. Okay, so anyways, so I hope you got the idea how to uh, find these characteristic number of characteristic roots. Just compare with this equation and find the b square minus 4ac. Okay, so I think that is clear, and we can now move to the question number 3. So we have this equation 2uxx minus 3uyy plus e to the power x ux plus u is equal to 0. So it is asking based on the number of real characteristics. This equation will be classified as what? Elliptic, parabola, hyperbola, or we cannot decide. The method is same, right? We need to write that equation. A u xx plus b u xy plus c u yy plus something else is equal to 0. Right? So now you can compare this equation with this equation, and what we find? We find a equal to what here in this equation? Coefficient of uxx. It is 2, right? And what is b? B is the coefficient of uxy. A So what is b here? The coefficient of uxy?
0.
0, right? There is no such term, right? And c?
-3.
C is equal to -3. Okay. So now you can easily find this b square minus 4ac. 0 plus 24. 24. This is greater than 0, right? This is
Hyperbola.
greater than 0. So it means it will have how many characteristics? Two real and different characteristics, right?
Yes, sir.
Two real and distinct. So this is elliptic or parabolic or hyperbolic. This is hyperbolic, right? This right? This is hyperbolic. Why? Because this is positive. Now, can you tell me the slope of these two curves? Now you are telling this is hyperbolic, and there are two real distinct characteristic lines, or the family of lines, two different families. So what will be the slope of those lines? Huh? Slope of characteristic lines. Simply you can write this equation: am square plus bm plus c is equal to 0, right? M will be equal to what?
dy by dx.
M is equal to dy by dx. And in this equation, a is what? 2. 2m square plus b is 0 and c is 3. So 2m square minus 3 is equal to 0. So m will be plus minus the square root of 3 by 2, right? So m1 is equal to plus root 3 by 2 and m2 is equal to minus root 3 by 2. Okay, so there are two families, and this is hyperbolic. Okay, I am I hope this is clear. If there is any doubt, then please ask, or we can move to this question. Question number 4. Okay, question number 4. It says unsteady diffusion equation with diffusion coefficient d given by dou u by dou t is equal to d times Laplacian of u. And we have options, 4 options: parabolic in time and space, parabolic in time and elliptic in space, elliptic in time and parabolic in space, elliptic in time and parabolic in space. So in space you can easily tell, right? In space it is Laplacian. So in space, it is parabolic or hyperbolic or elliptic.
Elliptic.
Elliptic. Why elliptic?
B value 0, A value and C value is 1.
Yes, B is 0 and A and C, they have some positive value, D, right? So it will be under root minus 4 D square, right? Some imaginary number, right? So there is no real characteristic in space. So it is elliptic in space and parabolic in time, right? In time, it will have one characteristic, right? It is a diffusion equation, unsteady diffusion equation. So this type of equations, you might have studied in heat transfer, right? So which type of solution this equation will have if you write the solution of this? Exponentially decaying, right? It will have exponentially decaying solutions, right? In heat transfer, you have studied, no? How do you solve this type of equation? We solve this type of equation using separation of variables.
Yes, yes.
You assume some profile. For example, you assume u is equal to some function of x and some function of time. Okay, I'm not writing this as function of y. I am taking only two variables. Okay, and then you do separation of variables and right. So the final solution you will get exponentially decaying. Okay. Now coming to question number 5. Question number 5 says the number of stencil points required for the calculation of a derivative in a second order central difference scheme is.
I think 3 points, sir.
Yes, 3 points. So stencil points are basically, it is the set of grid points which are used to calculate these derivatives or any other quantity. Okay. So it is saying a second order central difference scheme. So in central or order difference second order central difference scheme. For example, if you have a point I, then you take 1 point backward, right? I minus 1 and one more point I plus 1. Okay. And the derivative at this point is derivative at this point is it is I sorry ui plus 1 minus ui minus 1 divided by divide by 2 delta t, right? So delta t, or you can write it as h. Okay, so h is basically our delta t. Why we are calling this as second order scheme? Hello? Central difference is fine. Okay. Why central difference? If we are taking only I and I plus 1, let us say, then it would be forward difference. And if you are taking one point backward, then it will be backward difference. And if you are taking 3 points and I is at center, okay, so 1 point forward and 1 point backward, it is central difference. Fine. Why this term second order? What does this mean? Second order. In partial differential equations, the order meaning of second order was, order of derivative, right? D by dx is first order. D square by dx square is second order. But here, what is the meaning of second order? Okay. You know Taylor series expansion? Hello? Okay, before moving forward, I think we should discuss Taylor series. Okay, so that is the main thing. Okay, without Taylor series, you cannot write these central difference or forward difference or any difference scheme. Taylor series expansion. So the underlying concept is that uh, any function at a point can be written as a polynomial. Okay. For example, you have a function fx. Okay. So this function, the value of this function at point x can be written as some polynomial. So that polynomial you can write as a naught is some constant, plus a1x plus a2x square plus a3x cube and so on. Okay. So that's so we are writing this function as an expansion in the form of a polynomial at point x. Okay. This function can be anything. This can be, for example, sine x. Okay. So sine x, you need to write the Taylor series expansion of sine x or cos x maybe, or e to the power x, any function it can be. Okay. Now you have to find the values of these coefficients, right? You have to find a0, a1, a2, a3, and so on. Now, how will you find the values of these coefficients? If you can find the values of these coefficients, then you can write this function as the summation of these polynomial. Okay. How will you find? What will be a1? It is very easy. Okay. It is not difficult. How will you find a1? Sorry, a0.
Substitute x value 0.
Yes. Put x is equal to 0. Okay. So a1 is equal to f0. Okay. You have got a0. Now you need to find a1. So to find a1, what you can do is you just differentiate this with respect to x once. Okay. So it will be 0 plus a1 plus 2a2. Okay. Plus 3a3 x square and so on. And if you differentiate once more, it will be what? Okay. It will be 2a2 plus 6a3x and so on. Okay. So like this, you can find the value of any coefficient. Okay. So for example, from this equation, if you substitute x is equal to 0, then this will be your a1, right? And from this equation, if you substitute f x is equal to 0 in the second derivative, you will get 2a2. So a2 will be 1 by 2. Okay, like this. Okay, fine. right? So, okay. So using this concept, you can write the Taylor series expansion of a function fx about point C like about C, you can write it as fc plus times x minus C plus 2 times, right? C times x minus C squared divided by 2 factorial and so on. So in general, you can write it as sigma 1 by k factorial. Okay, starting from k is equal to 0 and it will go up to infinity. And f, and you will have to take the derivative, kth derivative of this f. Okay, and at point C, x minus C to the power k. Okay, so this is the Taylor series expansion. Okay, right? So in our case, this x minus C is h, and this h is very small. Okay, so as you take the higher power of this h, for example, you have h square, then this h square will be smaller than h. Okay, and it will be even smaller. Okay, so if you keep on taking higher power of h, it will become more and more small. Okay, so what we can do is we can ignore the higher order terms in the Taylor series expansion. Okay, so whenever we are writing this Taylor series expansion, we are not writing all the terms. Some terms we are truncating. Okay, we are leaving some terms. So uh, up to which degree we are taking, that is the uh, order of our scheme. Okay, so in this central difference scheme, we are saying second order central difference scheme. So this means this is accurate up to second order. Okay, right? Hello. So this means we are truncating from starting from h cube. Okay, and h square we are taking in the derivative. Okay, so it is more accurate as compared to first order, because in first order we are taking only up to h. Okay, and we are truncating from h square, but here we are also including h square, so this is more accurate. Okay, so if it was third order, then we will also include h cube, and we will leave the terms starting from h to the power 4. Okay, so that will be even more accurate. Okay, so as you increase the order of your scheme, it becomes more accurate, but it becomes more complicated. Okay, so it will take more time to solve. Okay, it will be more computationally complex. Okay. Okay, I think this should be clear. Okay, and maybe you can note down just one task. Okay, just compare forward difference and central difference and see their order. Okay, and if you are a little bit familiar about programming, then you just take some finite number of uh, iterations. For example, you can take 10 iterations, and what you will find, that central difference scheme is converging faster. Okay, Okay, anyways, coming to question number 6. So in question number 6, it is saying that a finite difference scheme for first order derivative. Okay, so this is first order is not for the order of scheme, not the accuracy. This is first order derivative. This means first derivative. Okay, with uniform mesh spacing h. Okay, the scheme uses a 3-point stencil xi xi plus h xi plus 2h in the forward differencing approach, so that the derivative can be uh, approximated as dxi by dx approximately equal to axi plus bxi plus 1 plus c phi I plus 2. I'm sorry, this is phi. Okay, so d phi. So at any I, derivative of this phi is equal to a phi plus b phi I plus 1 plus c phi I plus 2 by h. Okay, so h is our spacing, mesh spacing, and we have to find the value of b. Okay, hello. How will we do this? First, we need to write the Taylor series expansion. Okay. And up to which point? Up to h square point. Okay. Because there are 3 points, right? Hello. Hello.